Okay. Yep. Okay, thank you very much, Alberto and Roberto and Margarita. Thank you so much for, again, organizing a wonderful day. It's so great to be here and to talk about our common passion, molecular machines, motors, etc. And what I want to do is to talk a little bit about our work on molecular machines and also some very recent work to show what we have done recently. And let me start with emphasizing, I think, and Professor Balzani has written books about this, how important light is in Mother Nature. And these are two of my most favorite examples: photosynthesis, the fact that you can convert CO2 and make all the building blocks, and using light in this really complex machinery, and of course the process of vision, the fact that we can see each other, which is a molecular process in a very complex situation. I think it is really amazing that nature have evolved these systems of this kind of complexity with these crucial functions for life to make that possible. I also want to emphasize that we are not the first one to use light. Neither was it here, I think, in Bologna, because it was already Archimedes that used light in the Battle of Syracuse, fell before Christ. Then it was Leonardo who used, of course, a solar concentrator, which becomes popular again these days, how to concentrate solar. Lavoisier in France, who made 1800 degrees Celsius using his lenses to concentrate solar power. And then, of course, one of our real heroes, Giamiccian, who was well ahead of his time here in Bologna doing photochemistry with solar light. And nowadays this is becoming such a hot topic, of course. Let me also give credit to Vincenzo, because he is one of my heroes. I have been working on photochemistry for so many years, but I tell you, we studied most of his papers and his lessons that we learned from him. And we were so lucky when I organized in Groningen in 2001 the European Symposium on Organic Chemistry. One of the plenary speakers was Vincenzo, and Professor Balzani's lecture is remembered until today. It was a brilliant talk, and you see he was in good company, Barry Trost, K.G. Nicolau, and all these people. So thanks again, Vincenzo, for your great contributions, and not only because of your books, because this is a fantastic message for the whole society. So, having said that, it was mentioned already earlier, all the dynamic functions that we have in our bodies, in Mother Nature, etc. We as chemists are extremely good in building molecules and materials, but it was mentioned already the ATPase rotary motor, which was very early in evolution, then the bio-nanomotors that transport things in your cells, the ribosome, which is, for me, the most fantastic robotic system that exists in this world, the bacteria flagella motor, the optical switching process in the eye, as I mentioned before. These are extremely beautiful, but also very complex machines. But it sends also a clear message that nature evolved all these dynamic functions that make it possible that we can walk, talk, that trees can grow, etc. And of course, lots of people in the community, and I don't have to tell about this because all the heroes are here, the rotoxans and the catenans, beautiful examples of how to control motion. But there are many ways, of course, to induce motion in molecules. This, for instance, you have this ferrocene, like a ball gearing system, where you can control the orientation. You can, the early work of Aida and Shinkai, etc., that use these porphyrin systems to rotate groups with respect to each other simply by using acid-base reactions. The helical structures that could contract and expand, and we have seen beautiful examples from the Sauvage lab. And then, of course, Ikeda, who made these polymers with isobenzenes, and he really made a motor out of that by just making a polymer tape. And there are many more examples where people have tried to induce motion. But we all learned in our first year undergraduate chemistry first year class that when you have a single bond, there is rotation around this single bond. But this is not a motor. It's thermal rotation, conformational changes, and it's extremely fast. And Michael Kashiakariba realized, that when you make a system in a solid state, if there's enough space, you could rotate well over 100 megahertz. And of course, since then, these early days, there has been tremendous communities now that work on molecular machines and motors, etc., and it's steadily expanding and growing. And if you don't see your name, sorry, you can blame me for that because the list is way longer, I think. But what I really want to emphasize is we stand on the feet of giants before us that studied, rotary and dynamic behavior in molecules, etc. Although they were not motors and machines, they gave us lessons, they taught us important lessons. Like, for instance, already the people in 1922 and later picked up by one of the heroes of stereochemistry, Kurt Mislow, who unfortunately passed away earlier this year, biareals. And of course you can control rotation around biareals by inducing more steric hindrance. Of course there is no bias, it's not a motor, but of course it teaches us important lessons. And here you see the beautiful work of Miguel in UCLA. So there's another important aspect when you go to machines, and that is when you have a robot in a car manufacturing plant, we all know that this has a length scale of about 1 meter or 2 meters or so. This is the natural robot that I mentioned before, which is 24 nanometers in size. This makes the proteins in your body, at least most of the proteins. There's the effect of length scale. Here, size, mass, inertia plays an important role. We all know how heavy a car is when there is no fuel and you have to push it. Gravity plays a crucial role. In the nanoscale, molecular mass and gravity and so doesn't play much of a role. It's the flexibility of the system, the viscosity affects the interactions, the intermolecular, all these supramolecular interactions that we know, the interface phenomena, which are really important as well. So in the world of the nano, at the molecular world, we are at low Reynolds numbers, and of course it's much more about controlling motion because we have to fight Brownian motion, thermal motion, all the time. And so we work on molecular motors and machines with the whole idea of how can you go from molecules to dynamic molecular systems ultimately. And what do I mean by that? By inducing motion and also have then functions, more complex functions as part of a complex molecular system. And yesterday I emphasized that also. When you work on more complex functions, you need probably to bring in more than one molecule. You have to organize them, etc., at different levels. So the assembly, the trigger and response and motion, that is what we are very much interested in. And I will talk a little bit about rotary motion, surface confined motions, and about responsive materials. At the end, this is really important for the decades to come, is how to push things out of equilibrium or to operate far from equilibrium. We all know that if you have a piece of material here, this is pretty much in equilibrium. But our body is out of equilibrium. Don't forget that. If somebody tells you that you must be in equilibrium, don't. Be in balance or in harmony. But don't be in equilibrium because then you are dead. Living nature is out of equilibrium. And we have to learn in chemistry how to do these kind of things. And that can give us a lot of new opportunities. So I started in those days with molecular switches. And yesterday I talked a little bit about that we started with looking at the eye. This was 30 years ago. This is a beautiful process where you have a band molecule and a linear molecule. You switch between those states. There are millions of those retinal switches in your eye. It's a simple photochemical driven cis to trans photoisomerization. And that is the process of vision. The fact that I can see you and you can see me. Of course, it's way more complex, but the basis is a photoexcitation and a photochemical isomerization. And we thought, can we make information storage systems? This is how we started in those days. Of course, you cannot use these molecules because they are way too sensitive to build anything that looks like an information storage or a safe material or a computer or whatever. So we built these artificial switches. You see these two helical structures, a left-handed helix and a right-handed helix. These are still beam type molecules. Basically, it's a still beam. Look, here is a trans and here is a cis still beam unit. And we switch between cis and trans. And we avoided to do the photocyclization because this is a nasty side reaction of still beam photoisomerization, of course. And we made them chiral because we had the real problem of how to avoid destructive readout. And so we made a left-handed form and a right-handed form. This is the 0, this is the 1. We switch between 0 and 1 with light, 2 different wavelengths of light, as you can see. And that gave us a stable system that we could read out without destroying the information. Because if you have chiroptical properties, you can read out chiroptical properties outside the wavelengths where you do the switching. That worked pretty well. They're pretty stable. And then we made memory systems. We have been working on that with our physics colleagues, a different approach than Fraser followed. But I think there is a lot to be developed in that area of molecular information storage materials, etc. I think we have only scratched the surface. Switchable protein channels, because we build in switches in protein channels and we could contract and expand. We make responsive nanotubes where we could reorganize the supramolecular organization in these systems. But these are all switches. And I want to focus today a bit on rotary motion, because we spend a lot of effort on that. And this is, I think, the most beautiful rotary machine. And Jean-Pierre mentioned it already. If you think, I think Italians, like Dutch people, are very proud of their car. And I know you have a nice Audi. I have also an Audi. And I'm extremely proud of what the German engineers built, because these motors are fantastic. But I would argue here that this motor is way more sophisticated. This is my favorite motor in this world. And why is this? Because this is a unidirectional rotary motor. It can either consume ATP or it can produce ATP, depending on it rotates clockwise or counterclockwise. And believe it or not, these tiny nanomotors, there are millions and millions in your body. I think in every cell there are so many. These produce, as far as I know, almost half your body weight of ATP every 24 hours. Ladies and gentlemen, imagine how heavy you are. And these motors, these tiny machines, produce almost half your body weight. If people ask me, why do you need nanomotors? Are they any good for? Look at your own body. Can you imagine? You don't eat, the food in Italy is fantastic. But I don't, and you don't eat 40 kilograms of Italian food every 24 hours. So again, there is an important message. If industry tells us that you cannot recycle, one of the big challenges in society today and for chemistry to develop, what do you mean you cannot recycle? Your body recycles 35 kilograms or something like that every day. We just have to develop it and discover the chemistries, etc. Nature gives us clear messages. Okay, let me not deviate too much. This is a rotary motor. And of course, there are two fundamental questions: how to control rotary motion in the nano world and how to control left or right. Because imagine your car. If there's no preference for left or right, clockwise or counterclockwise, you stand still and you wouldn't be here if you came back up. Is there an equal probability you couldn't fall forward or backward? Either left or right, clockwise or counterclockwise, forward or backward. So we know how to do that because we can design chiral molecules, and here is the most beautiful example, which was called the Mona Lisa of modern science. I think even Italian people can agree on that. The right-handed helix of DNA. And so if nature used this chirality to control, for instance, directionality, we can explore it, and this is what we did in building these motor. I have to, once again, to emphasize serendipity is really important in science. We have been working on molecular switches back and forth for 9 years before we discovered that one of the molecules was not switching back, but it was switching forward. And when we realized that, we repeated the process and we could make a complete cycle, either clockwise or counterclockwise. And you see it rotating here. We excite the system, so you break the double bond, like the photochemistry in your eye, like this still beam photoisomerization, and you rotate through 4 steps in a rotary cycle. And why is this operating? Because we excite, so the energy comes from the light of double bond isomerization, and then we create a molecule that is less stable, it's higher in energy. And it does a helix inversion to stabilize itself. And in this molecule, there are 2 chiral elements. I have to emphasize that. Because if there would be only one chirality, you would not get directionality. We have 2 chiral elements, a diastereomeric relation. That is crucial. So we have the helical structure, and we have this metal substituent. You can see it's pointing in an upward pseudo-axial orientation. That's the stable structure. When we do the photochemical isomerization, we invert the helicity. The metal substituent is now in a pseudo-equatorial orientation. So it goes from axial to equatorial. This is much more crowded. The helix wants to invert, and it cannot go back so easily under normal conditions. So this is a forward movement. We repeat photochemistry, thermal isomerization, a 4-step cycle. And we can do it continuously. If we have one isomer, we can go clockwise. If we have the opposite one, we can go counterclockwise. It's 4 steps. We have the stable molecule. You excite, unstable or less stable. It does the helix inversion. You get lower energy. You excite again, unstable, and then you lower the energy again. And this makes a 4-step unidirectional rotary cycle. Here it rotates, and here, oops, we amplified the motion. And this is work we did several years ago. We amplified the motion by taking these motors as dopants in liquid crystals, so the materials that is in your display or your smartphone, and you can then control the chirality of this helical organization in the display material. This is the soft surface of the liquid crystal. This is a glass rod, which is about 10 micrometers. The motors themselves are only 1 micrometer, and we dope them with less than 1%. And you see the whole surface changes. The rotation is a directionality. This is all because of the amplification of the effect from the nano to the micro scale. So this was, for me, one of the most remarkable moments in my whole career. I will never forget. 5:15 on a Tuesday afternoon, students in my group came to me and said, "Ben, you have to come to the lab, we will show you something." There are not that many moments in your life as a scientist that you have this eureka moment. The students showed me there this setup. They switched on the lamp, and I saw the color changing, and I saw for the first time with my naked eye moving object, completely autonomous. I was speechless for 5 minutes. I didn't know what to say. This was a very emotional moment. Okay, you might wonder, this is for the synthetic chemist, how do you build such crowded molecules? And I tell you, we tried every olefination reaction in this world. The Peterson olefination, yeah, all the olefinations, the Wittig chemistries, cross-coupling, metathesis. But the best reaction is, I think it's going back to the good old work of Staudinger in Germany, and then developed by Barton and Kellogg. So we make this central double bond, which is very hindered, by taking a hydrazone, we oxidize it to a diazo compound, then we couple it with the thioketone. You make it 5-membered intermediate via 1,3-dipolar cycloaddition. Then you extrude nitrogen, and then you extrude sulfur from the episulfide. So what you do is you make 2 very reactive species, a diazo compound and a thioketone, and you then make a 5-membered ring, you contract to a 3-membered ring, and you contract to a 2-membered ring, which is a double bond. So gradually we introduce the steric hindrance, and that usually works pretty well. So initially our motor was only rotating once an hour, and we were extremely lucky, I think, because if it would have been very fast, we might have completely missed it. But it was very slow. Meanwhile, through structural modifications, and you can imagine what we have to do, we have to work on the thermal barrier of helix inversion, because that's the rate determining step. Meanwhile, we have motors that rotate in minutes, yeah, in microseconds, etc., etc. The fastest is 10 million rotations per second, but this is not reality. Eh? This is what the kinetics tell us. But of course, we all know photochemistry depends on quantum yield, depends upon the environment, you know, if you are on the surface or in the medium. It depends upon how much energy can you get in before you destroy your molecule. There's a lot of parameters. The photoisomerization is extremely fast. We teamed up with Steve Meach to do femtosecond laser spectroscopy to measure exactly those. Recently, as I have also studied inorganic chemistry as part of my master course, and we know very well the beautiful work here in Bologna and in Strasbourg and so, we thought, why not putting a ligand there in the base part, in the stator part, and now we can bind metal complexes, and through the metal complex we can tune the wavelength, and we can of course tune the speed of the rotation, because the barrier here depends upon the kind of metals we have here. And so now we have a real new series of types of systems where we can connect all these beautiful effects. We have to study carefully the literature now, because there's a wealth of information that we can explore in these systems. And recently we thought, do we need these two stereochemical elements in the molecule? Yes, you need that for directionality. But then together with Sander Wezenberg in our group, we thought, what if we make a simple system, a bridge still beam, with two binding units? And this has a very dynamic, this is a very dynamic system. That is to say, the helix can interconvert quite rapidly. But if we have here two thioureas, they bind chiral phosphates. So what we do now, we have a dynamic helical structure, and we have the chirality in an anion, a counterion. And this directs now, this shifts this equilibrium. And now when we power it with light, we can go through this cycle, and we can shift this equilibrium in a certain direction and control directionality in this way. And it works really beautiful. So you excite, you go from trans to cis, but then you shift the equilibrium due to the chiral binding, then you can excite again, and the ratio is 10:1. So we have a 90% directional preference. And then we found something very intriguing. We were very much interested for a couple of years already. How large can you make the groups attached to these motors to exert force when you go through solution or whatever? What parameters are important there? And we published on several of these systems. But here, what you see is we put these big conical shaped rigid groups, like the stoppers in Jean-Pierre and in Fraser's cases. And when you put two of these big groups here, these molecules start to form aggregates when you take a THF solution in water. And we get these beautiful balls. And you see they form micrometer size, very uniform type of shaped aggregating balls. And then when we add water, we can also follow it by fluorescence, by the way, because you get aggregation-induced fluorescence. When we add water, they contract to about 100 to 200 nanometer in water. And now the amazing thing. When we study, by all means, this pathway, we go through the four-step cycle. It follows beautiful the four-step unidirectional rotary cycle. As long as we don't have too much water, so at 60% water, we get beautiful the forward rotary cycle. There's enough space that they can do the helix inversion and they can move forward. But then when we contract further to the smaller aggregate, so to 200 nanometer, suddenly they start to rotate backwards. Why is that? Because you change the relative energies, so the barrier for helix inversion becomes too high, probably, that's our explanation now, probably to steric encumbrance in the system. So now depending upon how much water we have, we expand and contract, and we go from forward to backward rotation. We have to figure out what we can do with this, but for us it's really funny that you have this kind of way of control. And of course we are now in water. So we have been controlling motion on surfaces. I will say a little bit about that. In liquid crystals, in polymers. We have built a nano car. I think you saw this picture before, and I showed this yesterday. I'm not going to talk about it. Actually, what we did is, over the years, we have developed autonomous motion using these single molecules, these particles, rods you saw before, micro droplets. This is a bending nanotube. I hope you can see it bending. This is nanotubes that form tiny aggregates. This is not driven by light. This is driven by glucose. So here, this is sugar water, and this is a catalytic system that converts sugar, and the bubbles you see here is oxygen coming from the system. So this is propelled by sugar. So there are several ways to do autonomous motion. But let me, because I think we were a little late and I have to speed up maybe. Okay, I want to share with you a few of the things we have done in recent years that we got quite excited about. One is about surface confined motion, and we have been working on that for many, many years. because this was really tough. Initially, we built these motors with legs, tiles, for instance, on surfaces, and I think we should have gone to Bologna because it could have saved us 3-4 years of work. Because we made these systems, we put them on gold, for instance, but the legs were too short, and of course they didn't work at all because the energy was directly going to the surface. We got quenching, and they didn't work. So we made the legs a little bit longer, so to lift them up, and then we could make monolayers on gold, on quartz, on all kinds of surfaces with different anchoring groups, and we could get them working, you know, they were spinning around, and that worked really beautiful. And I showed this yesterday, we made this kind of windmill park powered by light. So we have now all kinds of responsive surfaces where you can move this around, and then you can do all kinds of tricks. For instance, we put a tripod here, as you can see. Now the axle is more or less parallel to the surface. There's a piece of Teflon here, fluorohydrocarbon, and when you expose it to the outside world or to the surface, you see that you can change the wettability, you change the surface thickness. You can do all kinds of tricks now to make responsive surfaces. And I think this whole field of responsive surfaces, once we know how to control motion or switch properties, you can control a lot of properties with respect to make smart surfaces, smart materials, etc. But of course, it's also intriguing how to position in 2 dimensions on the surface. And that was not easy until we had a nice discussion with Jiri Kaleta and Joseph Mikkel in Boulder, because they work on these crystals of TPP. And these TPP crystals, they have these channels. And they are very well defined because they are 1.5 nanometer apart, and they have channels with half a nanometer diameter. And Jiri in Prague designed these rods. There's a stopper here, a trypticine stopper. Then we put the motors there, and now we can assemble them on surfaces. And we have these motors now all in every channel, as far as we can tell. There is a motor, and they are now all positioned laterally 1.5 nanometer apart. So this is our stepping stone now to make concerted motion or synchronized motion, and see if we put dipoles or spins or whatever, can we then synchronize these effects? And Joseph has a keen interest in that. And then very recently, we were extremely happy that finally we succeeded to make these MOFs, taking advantage of the beautiful work of Omar Farah and the people in Joseph Hupp and so in Northwestern, where Fraser is, of course, and they have this beautiful way of exchanging ligands in MOFs without destroying the crystallinity and with destroying the MOFs. And so we built these motors with bipyridines, and we can exchange then the pillars in these MOFs, and we have now these beautiful 3-dimensional structures. So now you have this cube of sugar, crystalline, all the pillars. There are millions of these motors, and when you have enough space, we could prove that they rotate uncompromised and in a unidirectional sense. We had to use Raman spectroscopy and so to prove that, but it works really beautiful. So this is where we are with respect to condensed matter and surfaces. Now synchronizing motion. If you want to go to machines, we heard already about this, and we will see several more examples, I think, by Fraser. If you want to get to more advanced functions, you want to synchronize motion. And we discussed this in the group, and my students looked at the moon. And you might ask yourself, are these students in Groningen so romantic? Well, maybe they are, but this was not the reason. The reason was that if you stand on the Earth and you stand on the moon, you know, we always see the moon from the same side, because there is this locked or tidal lock motion. And we thought, can we make tidal locked motion using our motor? So the whole idea is you have a stator, you have a rotor, you bind a other rotor to it. In this case, we have the 2nd generation motor, which is light driven. We have here another rotor, a biaerial rotor. And now the idea is, when you go from this state to this state, there is a sliding motion. So you see this angle widens up from 60 to 120 degrees. And then when you go around, you see the same face. You see the same face always faces the black stator. And so we go around in this cycle, and of course this rotor has to have a certain motion, because otherwise it would not work. But it should not be free rotation, because then we lose the geared system or the lock motion. So it has to be a sliding motion where you change this angle and it goes around, 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 and you see it can go around in that way. And it works. I will skip this. We did all the spectroscopy, and so we made different isomers, by the way. You can make isomers where this points inwards, where it points outwards. We can go through all the cycles of the different isomers. And then we modeled it, and all the spectroscopy and measurements we did, we get this kind of lock motion. So we power it with light. It rotates in the unidirectional sense, and you see the moon. Yeah, the moon is of course, there is a bond to the moon here. But you see, you have this sliding motion, and it keeps always the same phase. This was a delicate design because the synthesis was not easy because it's a very crowded system, but you also have to balance the kinetics of these different pathways very well, and it worked very nice. So this is where we stand with this system. Now, to amplify motion, I will show you two examples. One, we go back to the beautiful work in Strasbourg. And I don't show your picture here, but you forgive me that I show you your great friend Jean-Marie Lane, a father of supramolecular chemistry. He made this beautiful helicates many, many years ago, 1987 as far as I know. And I got so excited when I saw this because these are beautiful structures. By the way, Jean-Marie was lecturing 3 years ago in Groningen. And you know Jean-Marie is also a great organ player. He's not only a master in supramolecular chemistry, but he was in our medieval cathedral and he played for 2 hours on this big organ from the 15th century. And I tell you, this is all manual. There's nothing electronic. It's amazing, you know. He played a beautiful concert for 2 hours. Anyway, so what we did is we thought, can we take this kind of ligands, attach it to the motor, change the helicity, etc., and it worked really beautiful. So we can go from left-handed helix to right-handed helix to left-handed helix because you change it, yeah? And you can, of course, go from this situation where they are expanded to the situation where they are close, and so we go from oligomers to monomers, change the helicity, go back to oligomers. So this is a way to make dynamic supramolecular aggregates where it's a self-assembly, you change the helicity, and you can push the system out of an equilibrium state. You can of course generate stationary states, but if you put in light, energy, you can push them out of the thermodynamic equilibrium. Now, another system it was mentioned also by Jean-Pierre is of course my friend Kisapone in Strasbourg, who took this second generation motor, used it as a kind of a cross-linker in a polymer, and he has now a piece of plastic that can move, contract, expand, contract, expand. And recently he published last year that he could go in the reverse order as well. So we really have now pieces of plastic. I wouldn't have thought it was possible 30 years ago. And it works. So you wind more or less, like a spiral, you wind up material. So my final small story is about cooperation and actuation in water, because we try to move to water and to interface with biological systems. That is not always that easy, but we were really interested in making a muscle. And I can be very brief because you got already a beautiful introduction about muscle function. It's the amplification of collective motion from the nano to the microscopic dimensions. And of course, many people work on it. I took a few other examples with responsive crystals by Erie, Dick Brewer and Bert Meyer. They work on polymer liquid crystals. Natalie Katsonis in Ikeda, I mentioned before, and Gisapone. But these are all polymers. The question now is to us, can cooperative, non-covalent interactions of small molecules support such an amplification to make a muscle-type function? Small molecules, can you organize them? And of course, we can look at Mother Nature, and what we did is we make these amphiphilic motors. I already mentioned it. You can make nanotubes. You hit it with light, you get vesicles. We get multilaminar vesicles. You go back to nanotubes. You can go through a cycle of self-assembled structures. And once we were realizing this, we realized maybe we can also organize these to make bundles. And what we did is we take this design. You see here a second generation motor. We put a long hydrophobic tail, two carboxylic acids. This is the architecture. These molecules self-assemble because they are amphiphilic molecules, and they organize in these fibers. But this is a gel. This is a gel in water, a hydrogel, because these form these nice fibers. But then, as Jean-Pierre already mentioned, in your muscles there's a lot of calcium. Nature uses calcium ions. And so we thought, let's take calcium. And calcium, of course, is it can accommodate two carboxylates. And what it does, it forms beautiful bundles of these fibers. And now you can draw a muscle. And this is what happened. Hopefully the movie works. We irradiate with light, and this is what you see. It bends. It bends towards the light. It can bend a wave to the other direction. If you change the direction of irradiation, you can make different... we can lift a small piece of paper. Of course, they are not very strong, but you can lift a piece of paper. What you see moving here is an aggregate of small molecules, a muscle. And what you see moving here, ladies and gentlemen, is 95% water. 95% water. Only 5% of the molecules. So this is our first attempt to make photoactivation artificial muscles. So this is small molecules, less than 1,000 molecular weight, 5 weight% needed, activation in water and air. We have a large amplitudinal motion. We get precise control over shape by the light, and it's capable to do some mechanical work. That is, we cannot lift a stone, but we can lift a piece of paper. So maybe soft robotics in the future. There are many approaches. This is an emerging field, very attractive, and I know some people here are very active in this field. So finally, it was mentioned calcium. Maybe there's a good reason that nature discovered to use calcium. Look, we used all kinds of metal ions. Calcium sticks out tremendously. This is only about the motion. The calcium works beautiful, much better than all the other ions. So this is where we stand at this moment. I want to finish by saying that we start to program molecules, we get responsive and adaptive functions, and we go to motion and ultimately dynamic systems. And I think, inspired by Mother Nature, we don't have the limitations of the molecules of Mother Nature. We can design our own molecular world with new functions, and that might lead to switches and motors and machines for information storage, responsive materials, smart surfaces. I didn't talk about precision therapeutics, but for instance, roofing sensors, soft robotics, nanoscale energy. There's a lot of opportunities to discover. And so I couldn't have done anything, wasn't it, for my fantastic team of young stars that make this all possible. All the students, co-workers in the lab, of course the funding agencies, but these are the real stars. And I must say that every day it is a delight and an honor to work with all these young students in the lab. And if you think there is nothing to be discovered, let's remind Francis Bacon's words. There are ill discoverers that think there is no land when they can see nothing but sea. There are tremendous opportunities. And so I value that we have a universal language. That's the language of the molecules in chemistry. That we share international cooperation, and I'm so glad to be here. That we have no borders. Let me emphasize that. We go beyond frontiers. And we share a passion. And I want to finish with my hero, your famous countryman, Leonardo, who said, where nature finishes producing its own species, man begins with the help of nature to create an infinity of species. And especially for the young students in the audience, imagine the unimaginable. Thank you so much.
Thank you very much, Ben, for this fantastic lecture, and also for pointing out that science provides an example, maybe the best example, of the positive effects of globalization. No? When we speak about globalization, it's normally to emphasize negative effects, but in the case of science, it's really a remarkable example of how good can be, to share things and people. Okay, so we have time for a few questions, if there are, from the audience. I think that Ben will be happy to answer. Don't be shy.
Yes, please.
One question, two questions. Lucia first and then Enzo.
Very nice and very inspiring work. And maybe it's just a future. Nowadays, we are working a lot trying to control the movement and the rotation. But I know there is a lot of people also trying to get the control of the movement, or maybe the chirality, by moving far from the thermodynamic control to the equilibrium control, not having anymore the stochastic balance, and going through getting an enantiomeric excess. So the Vietnam ripening and... So my idea is like, is it possible in the future, maybe with one of your rotor, not inducing the chirality inside, but trying to get it from outside response?
That's very interesting. How to get the chirality or the chiral bias. Now we build it in, or we just have also used the supramolecular approach. Then you can imagine that you would also take advantage of a chiral surface of quartz, for instance, or some other chiral bias, or using, for instance, circular polarized light. We did that, not with the motors, because no student in my group wants to do it, and I tell you why. Because we published a paper many years ago about these switches, when we made these switches, you know, with light, and we used circular polarized light. Now, that works. You can get a chiral bias, as you expect, theoretically. And we got 0.06% EE. Now that's difficult to prove. That cost us a lot of time to prove it. But we amplified it in a liquid crystal, and then we could see it, actually, that it forms a chiral phase. Now my group is also doing quite a bit of work on asymmetric catalysis, and usually we say, when you have 90% EE, we can maybe get a publication these days. This is the standard. No, 0.06% E is not much, but you can predict it by the good anisotropy factor, the G factor. You know that in these compounds that have all allowed transitions, pi systems and so, the G factor is very low. So yes, you can use different ways to link chirality or to control chirality. We also use these systems to make chiral catalysts. I had no time to show it today, but you can change the chirality and you change the outcome of a catalytic reaction. And we use it also now for other phenomena. It would be great if you could induce crystallization and crystallize one form or the other or so. We have not done it, but thanks for the question. Next week there will be a conference actually in Brussels on fundamental aspects of chirality, and I'm going there as well, and I'm looking forward to discuss with the people. Thanks for the question. There was another question here. Yes?
Yeah, Enzo Palermo.
Yeah, thanks, very nice, very nice talk. And what I find more remarkable is the kind of progress that you can see from having a single motors in solution to having an entire crystal where they are precisely arranged and they can really move. And to me it seems that this thing can have really lots of even interesting application. You showed some initial example of actuation, but I guess also nanofluidics or controllable wetting, or I don't know, I cannot think.
Sure.
What do you think are the most interesting or potentially viable of all these possible application that this new technology opens up?
Yeah, the possible application, this is always a difficult question because you don't know what kind of, but I would say the fact that you have dynamic and responsive systems, maybe responsive surfaces, coatings or glass, you know, that clean themselves, or wettability, or self-healing materials. This field goes very quickly now. I think this was discussed also briefly yesterday. I think in 15 years from now, maybe 10, 15 years, you will see the first materials, and actually around the world there are several groups working on there to take responsive surfaces, responsive coatings, and also self-healing materials. And I would say there are lots of opportunities. To make real robots and so, soft robotics and so, is maybe a little bit longer distance and machines. And realize also, the people here, the groups that you hear today, we were trying to develop fundamental principles. How to get control over translational motion, or rotational motion, contraction, expansion, these kind of things. Of course, the molecules, in some cases like my molecules, are way too complex. But once you know how to do it, you can think about simpler molecules or different approaches. The first plane that was built by the Wright brothers, you remember? This very primitive plane. And the Airbus that they built in Toulouse these days. The design is, and the materials are pretty different, eh? And I would say the Toulouse plane, the Airbus, does its job way better. It might take a while, but once you know how to fly, you can build a Boeing or an Airbus. Please go ahead, take the opportunity.
The third quick question from Valentina, in the back, là dietro, guarda Martina.
Okay.
Okay. So I have a curiosity about the fact that in the cell membrane there are a lot of actuators and mechanosensors. So I was wondering, maybe it's a trivial question, but I was wondering whether there is any evidence of the ability of these molecules to modulate the mechanical movement of a cell membrane.
Oh, yeah.
And in this way you might think about modulating some important functionalities that you mentioned before.
This is really important, you know, the question, can you link up with cell membranes and those things? What we do is building motors that work in water, so we can maybe then have them getting into the cell. We are also working, one of my postdocs who works on this missile is now working on systems that penetrate into cell membrane. But we have not we get some very exciting results, but I cannot talk about it because we have to do all the controls, etc. James Stewart in Rice University published this earlier this year, a paper where he has taken one of the motors and he drills a hole in a cell membrane to deliver an anti-cancer drug. You should read that paper, it's really interesting. So there are first examples coming where you take advantage of a mechanical effect, for instance, in a cell membrane. And these are, of course, interesting opportunities, because you can do things that you couldn't do before. So like a corkscrew, you know, screw into a membrane or so and drill a hole. I don't know how good it will be, but the first example, James Stewart, read his paper.
Okay.
So thanks for the question.
Okay, so I think we can stop the discussion here. We are going to have a little break and we start again at 11:45. 11:45. Well, let's thank Professor Feringa once again.